Good afternoon, everyone. I'm Ying Zheng, the Director of Asian Initiatives at Western Michigan University's Haneke Institute for Global Education. I also serve as the Director of Timothy Light Center for Chinese Studies. Welcome to Timothy Light Center's webinar series of Fall 2021. Today, we're honored to welcome our guest speaker, Dr. Jinfa Cai. Kathleen and David Hollowell, professor for math education in University of Delaware. I would like to invite Dr. Jianping Shen, the co-director of the Wallace Foundation Grant and professor of educational leadership and evaluation, measurement and research, to introduce Dr. Cai to us. 沈老师，请。
Thank you, Ying. It is really my honor to introduce both my colleague and friend, Dr. Jinfa Cai, to give us a talk on math education. I have known Jinfa for many years. We started our career essentially at about the same time, meeting at the AI meetings in those early years. So Dr. Cai is now currently holds math education endowed chairship at the University of Delaware. It's the Kathleen and David Hollowell Professor of Math Education. He's also a fellow of American Educational Research Association, and he served as the editor-in-chief for the Journal for Research in Mathematics Education, the top research journal in math education around the globe. In 2018, Dr. Cai received the Weber Award, honoring his significant contribution to the state of Delaware. He also served as a program director at the National Science Foundation. And in addition to all those roles he played, he also served in the K-12 system in various kinds of capacities. So it is indeed my honor to introduce Dr. Cai. He's a very well-known math education researcher. So while he's making the talk, feel free to pose questions in the chat box. And his talk will last for about 1 hour. And we will have about half an hour for.
You muted yourself.
Oh, my goodness. No one reminds me. So should I introduce you again?
No, that's okay. It's only the last sentence. That's perfectly fine. Thank you so much.
Okay.
Jianping. Yeah.
All right. Okay.
And Ying, thank you so much for that. And I will just go ahead and start. Okay, good afternoon, everyone. So once again, I thank you all for coming. And also thank you for the opportunity to share with you. And in particular, I have 3 friends now, and I get to know them, and for inviting me and make all those arrangements. And I received quite a few emails, the step-by-step, which is lots of relief, my sort of like a burden to have to remember this or that. So I greatly appreciate that. In fact, the mailing even reminded me yesterday so that I would be on time and so forth. So for that, but the topic I was almost like given. It's like a task to sign to me to talk about, because I have been doing some cross comparative studies in mathematics education. So I decided to choose this topic to improve students' learning. But we talk about the East and the West, how we could learn from each other. So I will in that kind of sense to talk about this series of studies I have been doing. So that's the main focus for today, which means that even though teaching or instruction is a culturally very embedded kind of activity, sometimes it's very difficult to transform one effective practice from one culture to another. But we really could serve as a mirror to examine ourselves so that we could learn from each other. But eventually, our goal is to improving students' learning of mathematics. But some of the issues I'm going to talk about could go beyond mathematics, even though I'm going to use studies from mathematics education as like examples to make my point. So in particularly, and I want to draw the research from the 3 lines of the work I have been doing. So over the, as the Jianping already mentioned, we know each other for a long time, and we started career probably almost at the same time. So it's been a while. So in the past 20-something years, I have been involved in 3 research projects. The first one is cross-national comparative studies. I started with my dissertation is on this topic. Then I continued. Later on, I did a longitudinal study about the curriculum. Then in the past 10 years or so, I started to work on a project on mathematical problem posing. So I will draw a little bit from here and there to make my points, okay? So the 6 points I'm going to make, 6 points I'm going to make, okay? So there is a little sort of a caveat I want to mention in here, which is that for educational research, even though this is very practice-based, but in the past, so many years, we produce lots of research papers, but there is a constant tension between research and practice, which means that sometimes the research studies we work on couldn't directly apply to the school settings to improve students' learning. So that connection is constant effort we need to have. So what I'm going to do today is based on a series of studies I have conducted, try to point out a few things or few insights we could use to improve students' learning. So I summarized into these 6 of them. Hopefully I will have enough time to go over them. So I'm going to use the study here and there to make these points. But because of the timing limitation, so I will not talk too much about the background of each study. And if later on you want to know the particular study about the background, the research methods, and so forth, you could always send me a note in the chat, and I would be more than happy to talk to you, either today or privately through emails, and I could send you the full paper if needed. Okay. All right. So I'm going to go through one by one. So now I'm going to go to the first one now. The first one is really that mathematics is multifaceted, especially involving the thinking and the learning. So if we simply to divide that into different categories, we could view the computation, problem solving. And the problem solving also could be viewed as a routine problem solving or the non-routine problem solving. But the first insight I want to share with you is that having computational proficiency and routine problem solving skills does not necessarily having non-routine and creative problem solving. So the implication is that if we want to develop students' thinking, we have to ask what kind of thinking we want to develop, foster their development. Is that computation? Is that routine problem solving or non-routine problem solving? So let me share with a couple of studies. Okay, so this study is conducted way early on. It's in 1997, 1998, or 20 something years ago. So at that time, I examined 6th grade US and Chinese students' performance on 4 types of tasks. 13 computing tasks is purely naked computation, very simple kind of driven. For example, it's the 1 3/4 divided by 1/3 equal to what? Computing items. Second one is I call simple word problem solving tasks. 18 of them. So this 18 items that I adopted from the Richard Mayer, who is I think is from the Santa Barbara and the UC system. And he developed a model about the word problem solving, which involved 2 major aspects. One is related to understand it, Another is really trying to represent the problem. So based on his model, he developed an instrument. So adopted 18 of the items from him, which could assess simple word problem solving skills. And then I have 6 process constraint problem solving tasks. Now this task is more complex. And later on, actually, I could show you examples, but for now, you just given is more complex than the simple word problem solving tasks. But for these 6 process constraint tasks, always could have a formula to follow or to be used. But the fourth category, which is called process open tasks, which are truly open and they know given algorithm or obvious algorithm students could use to solve the problem. So it's more open. So those are the 4 types of tasks. So 20 years ago, that's the results I received. So I have a sample of the US 6th graders and a sample of the Chinese 6th graders. Well, I'm not going to ask you to observe now, and if I'm in person, we'll talk over. But since online, so I will quickly just point to the few things. One thing is that if you look at it on the computation and a simple word problem solving, and even the process constraint problem solving tasks, Chinese students are performing way better than the US students. That's the one observation. Second observation is that Chinese students tend to decline from the perform pretty well on computation to the become the 57% of the students will be able to solve those process open complex problem solving tasks. So just when the open, the less successful. Well, that's second observation. The third observation is that US students sounds like all low for the first 3 type of items, but on the fourth one, it's actually better than Chinese students. Now, in this fourth category here, even though the percentage-wise is very small, but it's still statistically significant, different. So the question is really this. So if I could use a metaphor to do that, use a building and a foundation. The foundation is certainly supported the building, but the foundation has no usage. There's no space to be used. But the building itself, there are rooms, there are spaces could be used. So use the similar kind of metaphor, computation and routine problem solving, we could consider as a foundation, which then supporting the non-routine creative problem solving skills, which could be more useful after they graduate or in the workplace or in the certain innovations. That if we do that kind of metaphor, if allow me to do that kind of metaphor, is that then if the foundation is too strong, and with the material, then we have a less space for that. Otherwise, if the foundation is too weak, then we couldn't support the entire building. So the question is that foundation and the building, if the resource we could use, hopefully would be just right. So which means that where is the balance for this? So it's the total investment is fixed now for this. So even though I couldn't answer this balance question, but to me it's clear that based on these results, perhaps the US students could have more opportunities to learn those basic skills and computation, develop those computation skills, and understand why that works. And the Chinese student may need to have more opportunities to engage in those process open tasks for that. So about 20 years later, just about in 2017 and 2018, I have used the same items. I sampled the students in the same schools. I sampled 20 years ago, to did the replication study, give to those tasks to the same group of students, same group, or the students from same school, the different group of students. I'm sorry, I said wrong. Okay, I said wrong. From the same school 20 years ago, they are sampled in the same way in those same schools in China. And I did the analysis. Well, 20 years later, well, the first two type of tasks, it did decrease a little bit. But in the advantages in the third type of tasks, especially for the fourth type of tasks, actually increased dramatically. Well, the explanation would be that in the past 20-something years, the China has involved in the quite a bit of so-called educational reform, and the new textbooks has been developed, and with more those kind of so-called process open tasks. If we analyze the textbooks, it could be very easily could be seen those kind of learning opportunities provided for students in the textbooks. Well, so this is the go back to my original point. Mathematical thinking is really involves different facets. So we want to develop students' computation skills, but in the meantime, we also want to develop their other type of high order thinking skills in mathematics. So the goal is that hopefully will be balanced in different type of thinking skills. In this case, in the 20 years later, in these application studies, even though on the first two type of tasks sacrifice a little bit, because the time they put into learn those computation and simple word problem solving reduced, but more time on later one. So those kind of compensation, it is worthwhile. Worth the more opportunity for them to engage in the third and fourth type of problems for that. Okay, so that's the first insight I would have. But some of you may be asking me, what about a US student 20 years later? I still haven't got funding yet to do an application study for the US students. Once that's I have secure funding, then I will also replicate that part of the study. Maybe that's in the near future, hopefully. All right. So now let me go to the second insight. Okay. Second insight is that concrete experiences do not automatically lead to generalization and conceptual understanding. Now, in mathematics, we all know that it's abstract. So we want to provide students a little bit more concrete kind of experience so that they could make sense of it and then lead to the generalization and understand symbolically even. Okay, but the insight I want to provide is that concrete experiences do not automatically lead to generalization and conceptual understanding. In between, need teachers' effort in classroom to help students make such a transition from concrete experiences push up to the generalization and the conceptual understanding. To make this point, let me share with you a few findings. Okay, now this is a Hertz problem. By the way, this problem is I call it a process constraint. problem, which I mentioned in the first insight. So this problem is that it's, of course, dealing with the average. Okay, the first 3 weeks got a number of hats sold listed here. Now the question asked is that how many hats must Angela sell in week 4 so that the average number of hats sold is 7? Show how you find your answer. Okay, so the student could have different ways to solve it. They could use formula. The formula could be used is arithmetically. You know, the average is 7, 4 weeks, so 4 times 7, and take away the number of hats sold in the first 3 weeks, so which is 10. Or they could solve it algebraically. Assume the number of hats sold in week 4 is X. Then the number of hats sold in the first 3 weeks plus X should equal to 7 times 4. Then solve for X. Then some student also could solve this way here. So this way is that, so I call the leveling approach. So the average is 7, right? 7 is the average. So here the week 1, we got a 9. So we got 2 extra here. So we move down to the second week. And the third week only got 6 hats. So need 1 more. But the second week also needed, after move that 2, still need 2 more. But those 3 more will come from the fourth week. Fourth week will contribute to it. But it still needed the 7 for itself, right? So that's leveled now. So the average will use this line here, leveled, each week became the 7 now. So average is 7. So students also could solve that way. Will make a lot of sense, right? Because that's what the average is really about. Okay, so I analyzed the US and the Chinese students, those kind of strategies they used. Now this is the percentage of the students used different strategy or representations here. In this case, I'm talking about strategy and representation interchangeably, okay? So use algebraic approach, set of equations to solve, and have 1 US student did it, but because of rounding, so only 0 here. Actually, there is 1 US student use algebraic equation. 59% for US students use arithmetic. Then the 8% use pictorial representation or pictorial strategies. And the rest of 33% use the verbal explanation. They use the written words to explain how they solved the problem. And the bottom is the Chinese students, So very clearly, the kind of strategies students use between the 2 groups are quite different. So I did an additional analysis because these students also solved another 10 mathematical problems. So I used another 10 mathematical problems as a measure of their math performance. And I want to see, how the students use different strategies. They perform. So let's look at this table here. So this is the mean score here on the 10 tasks, okay? So arithmetic, algebraic approach here, the mean is 31 for that single US student. But for the Chinese students, got 58 students use this approach, 26%. But gradually, it's arithmetic and word is a little bit worse. And they know Chinese students use the pictorial representations. So in this case here, is that somehow, if we just look at the US students here, for those use arithmetic approach and algebraic approach tend to perform much better than those students who use pictorial representations or use the verbal representations. So my hunch then is that, it's a pictorial representations or even the verbal representation need one more step, one more push to get into this algebraic representation and arithmetic representations. To make this point here, let me show you another task. Okay, this is another task from one of the studies. This is a pattern problem. Says that Sally is having a party. First time the doorbell rings, one guest enters. Otherwise, 3 guests enter, 5 guests enter, and 7 guests enter. Okay, so 2 major questions ask them to do. First one is that how many guests will enter on the 10th ring? And the second major question is that if 99 guests enter on one of the rings, what ring was it? What ring was it? Now, the results for the first question between the 2 groups are quite similar, the successful rate. But for the second major question, we got 43% of Chinese students got it correct, but only 24% of US students got it correct. So then we look into the strategies. So this is one of the strategies students used. Okay, because they generate a general kind of formula. It is 2 times ring minus 1, which is 2n minus 1. The n is represent the ring number. And 2n minus 1 equal to 99. Then set this up and the answer equal to 50. Okay. Then another approach you could do, because it's really increased by 2. Keep going. So some of the US students even just list all of them up until the 99, until the 50th ring, then get the 99 guests entered, and then put the 50 as the correct answer there. Now that's viable approach, and understand that it's increased by 2, but it's in the very concrete level. So it's based on my analysis, the reasons US students got small proportion of them correct, because in those kind of concrete ways, they will not be able to correctly list all of them. So they yielded the incorrect answers. Okay, so in this kind of representations, I call it concrete, but from this to these strategies, I call it somewhat the generalization. So in between the two, to me is that it's not automatically, if a student be able to use this approach, could lead to the other kind of generalization. In between, need to have steps to help students to make that kind of transition. It's not automatic. The reason I make this point is that there is enough evidence showing that some of the US students think that such kind of concrete representation or concrete experiences could automatically lead to the generalization. To make this point again, so I could show you another sort of a study, another little study, okay? Go back to this average problem. So I was talking about that different strategies there, right? Got the response A, which use equation to solve it. Okay. Response B is use that pictorial representation to solve it. And response C use those arithmetic approach to solve it. So what I did is that I asked a group of the Chinese teachers and a group of the US teachers to evaluate them. I give them a scoring rubric from 0, 1, 2, 3, 4. So 5-point scale from 0 to 4. And I ask them to score each of the response. Here the results are received. Here the received. So for the response A, oh, I said it wrong. Response A should be algebra. I think response A should be algebra. Yeah. Okay. So this is a, let me quickly correct it. Okay. Response A is algebraic. And the two groups are actually similar. Response B is arithmetic. If you look at the Chinese teachers, is from the highest score, possible score is 4. Oh no, I'm making quite a bit of mistake here. The second one should be pictorial. My apology. Okay, so that look at the for the A and the C, for the Chinese teachers are really similar, but they scored the B. Okay, let me go back to the B. B is this kind of pictorial. Okay, I made a mistake. I labeled it wrong. So for the B is actually significantly low. But look at the U.S. teachers reading is 3.85 is the highest compared to other two. So in this case is that looking at the Chinese teachers, they even don't accept. Some of the Chinese teachers even don't accept the pictorial representation as the appropriate solution strategy. Look at their variance. Look at their standard deviation. Standard deviation here. The standard deviation is a little over 1, but for U.S. teachers, it's a 0.364, so which is quite uniform. But for the Chinese teachers, some of them get the 4 points, but lots of them, considerable number of them even give 0 points for this B. So all over the place for this. So there is no sort of a uniform understanding about how to evaluate this response B. Okay, the point is this here. So the Chinese teachers is really trying to facilitate the development of using arithmetic approach and algebraic approach. But for US teachers, as long as they could solve it, it's fine. Now, to me, in evaluating those students' responses, I would be perfectly fine to score the response B will be perfect score. I'm fine with that. But the point I'm really trying to make is that if we just stay in the pictorial level, it's not enough. We could build on that to reach the generalization, the arithmetic and algebraic approaches. Otherwise, if we stay in the B, if the numbers is changed, become huge, it will be very difficult for students to join, make those joins for that. All right, so this will automatically lead me to the third point I want to make now. Students can think algebraically in early grades. So in the United States, we always say that algebra could be gatekeeper. If we look at the textbooks or curriculum, the students in other countries, especially in Asian countries, are learned algebra, even formally learned algebra much earlier than students in the United States. So, but there is enough evidence to show that students in any country, including United States, really they could think algebraically in much early on. So I'm going to also say a few words about that. So I'm going to talk about it as this LaCal project we worked on, and about starting in 2004. it lasted almost 7 years in terms of funding. So we got 2 grants to work on this project. And I think this is the only project we have the longitudinal data from the 6th grade all the way to the 12th grade data. When there are 2 group of students using 2 different type of the curriculum materials. The one type of curriculum materials is called come from the Michigan State. It's your neighbor. It's called Connected Mathematics Project. So I call that as CMP. So the goal for this project is to longitudinally investigate the effects of the CMP curriculum on students' learning of algebra to the effects of more traditional middle school mathematics curriculum. So the reason I use this to give you a little bit snapshot is that because this curriculum have a very nice way to introduce even 6th grade students to think algebraically. So this is the very first problem CMP curriculum used to introduce the valuable ideas. Now, as we all know, that the variable idea is such an important concept in studying algebra. So this is use the real life situation to looking at the one changes could lead to another change. That's the variable idea here. But if we look at the non-CMP curriculum materials in 6th grade, it's really the variable idea is is a total different kind of way. This is to evaluate algebraic expressions. If B equal to 25, what is 16 plus B? So it's a quite different way to do that. Okay. But of course, I'm favoring would be this kind of approach to introduce the algebraic ideas. Let me continue with this. So CMP curriculum material even very formally defined a variable as a quantity that changes or varies. But for the non-CMP curriculum materials used in the USA, variable is defined as a symbol, usually a letter, used to represent a number. So it's more like an unknown kind of way to define it. And equation solving in algebra, equation solving is also so important. See, look at the CMP is not only to looking at the steps about solving equations, but correspondingly use real life situations to make each step meaningful. For that. And so in terms of definition of equations, is the CMP use the functional approach to define it. But for the non-CMP one is that says that equation is a sentence that contains an equal sign. So it's really the equation is viewed this as unknown, for this variable. But in the CMP approach, since use functional approach, viewed the equation as a certain point in the function, needed to figure out another variable. So that in the CMP curriculum material, because of that kind of conceptualization of algebraic ideas, see, got this one equation and one variable, those kind of the tasks in the textbooks, over 93% in the 3 middle school years. But in the non-CMP curriculum materials is purely on the one equation, one variable kind of activities. So in this sense, would it be in terms of algebraic ideas would be much more meaningful because usually embedded in the context. Or each step of symbol manipulation, trying to have a meaning to attach to it. Okay, so this is an example for the U.S. middle school curriculum, which that could have existing materials that could help students to develop algebraic thinking skills. Now I'm going to also introduce some activities from East Asia. So this example is come from Singapore. By the way, I also studied the early algebraic thinking in the Singapore, South Korea, and the Chinese mathematical curriculum materials. So this one is from the 4th grade Singapore textbook. If we quickly look at this problem here, this is a very sort of simple kind of arithmetic problem. But in Singapore materials, they introduced a special kind of way to solve this problem. Now, people use different terms to call this. Some people call it pictorial equation. Some people call it tape diagram, but it does not matter, whatever we call, okay? So those kind of way to represent the relationship would help students to learn the formal algebra. Because in this case here, could view this block as a variable x. So this is x as well. So the algebraic idea is really trying to use symbolic representations to represent different relationships. So in this problem, there are a few relationships here. So look, first relationship is this. Mei Fan and Su Hua have 2,000 stickers altogether. So altogether, they have 2,000. But Mei Fan has 600 more stickers than Su Hua. So that's second relationship. So this is 600 more than this one here. See, use that two relationships could set up an equation to solve it. But to help students to be more accessible to later on for the X, use picture to represent it, the unknown for that. So this approach find it to be quite accessible even for the US students. And we tried a few in different classrooms. And we also could use prompt posing to do that. So instead of asking them to solve this problem, what we could say is that, please pose a word problem which can be solved using x plus 3 equals 10. So, usually we give the word problem to students, ask them to represent use an equation, then solve an equation, then answer the problem. So use a prompt posing approach, we just go other way around. Give them the equation, ask them to come up with word problem. Now, we don't have to use this x to represent unknown. We could use this as well, because they pose a word problem which can be solved using parentheses times 5 equal to 75. This kind of equation. So the number in the parentheses times 5 equal to 75. Now, in this kind of way, students will have the opportunity to make sense of this equation in the word problem. What does this x really mean? What does this parenthesis really mean in the word problem? Now, those kind of approach would help students to think algebraically, even in early grades. And a number of us, we put a book together. It's really to looking at the develop algebraic thinking for elementary and middle school students. So the major idea is that the algebra and arithmetic are the boundary is not so clear, because students can be guided to see algebra in arithmetic. One of the challenges students have for studying algebra in this country is that separation of the arithmetic and algebra. Now this is arithmetic. Now we need to study algebra. Two things separate. So develops certain kind of anxiety to study algebra. But nowadays, the algebra and arithmetic, really two things are so closely related to each other. We even could guide students to see algebra in arithmetic. A number of scholars in this country are doing it. There's some of them from the medicine, there's some of them from the Turk and EDC in Massachusetts, the two research institute, also work on those kind of ideas, All right, so that's the third one. And I'm going to the fourth one now. I guess I needed to be fast a little bit so that I could finish up. Okay. The fourth one is that prompt-based instruction has a positive impact on students' attitudes towards mathematics and achievement. So which means that learn mathematics is not just procedures, symbol manipulations. The prompt-based instruction helps students to go beyond symbol manipulation and the procedures in their learning of mathematics. Okay, so this one I just share with you one study, and to make my point. Okay, this study is about attitude. We did it in for the 1,300 high school students. Those students are in a different track. And 285 are non-college preparation students. 858 are the college preparation students, but they are using the traditional math curriculum. But 173 use the so-called reformed curriculum materials. So these students, the students from this school have been engaged in a project funded by NSF and try to training teachers over the 3 or 4 years to using those so-called National Science Foundation funded curriculum materials, as well as the series of the teacher professional development for that. So one thing we want to figure out is that, how students view about mathematics. Because the prior study always says that students, it's not so positive about mathematics. So we used this instrument instead of use the, agree, disagree, those kind of likelihood kind of items. So we present says that math were food, it would be what? Because here's the reason. They have to provide the reason. If it's a color, what kind of color it is. If it's animal, what kind of animal it is. They compare to the mathematics, and they have to justify the reason. Okay. So I give you some of the students' responses to show, because this instrument worked out so well, because it provided the verbiage for students to describe their thinking inside about mathematics. So here is the one. It says the purple is my favorite color. It's my birthstone color, plus it brings passionate. That's how I feel about mathematics. And another one is to show that mathematics, how they like mathematics here and why. One says that, okay, math is like steak, because math is a full, expensive subject. However, like a steak, there are tough bits of gristle and very difficult to chew to get it in the process. But a full meal is very satisfying, even though the process is very challenging to eat a steak. Also, it could be the vegetable. Say that, okay, vegetable is good for you, but even though sometimes it's not so taste, but the healthy life needs vegetables, See, those kind of students are engaged in that. Some of them said mathematics is like a mosquito, because whatever you do, try to get rid of it, but it's always come back to you and follow you. You have to study it. At the University of Delaware, we only have one major. One major does not require any math credits. So it is like a follow everywhere. See, look at these students, it's viewed as so negatively about mathematics. It's like gum. It's like gum, tasteless, worthless, does not have any nutrition or vitamins. So we scored them, and both quantitatively and qualitatively. Here is the quantitatively at about attitude level here, attitude level. Now, look at the purple one is non-college prep, college prep, but use traditional curriculum materials. College prep use so-called NS-funded reform curriculum materials. So look at that. So student, every group of the students have the 0.1 and 1 and 2 here. But for those who using the NS-funded curriculum materials, in general, their attitude tend to be more positive. Because look at that level 3, 4, and 5. Its total is the proportion wise is greater than the other two groups of students. Now, the reason I show you this study, because of this NS-funded curriculum material is considered as prompt-based kind of curriculum materials. So once we engage students in challenges, difficult problems, even though it's harder to learn, but actually it could be eventually, once they feel successful, they could turn to be more positive towards the mathematics in their attitude, And I'm going to skip this a little bit here. So the overall, the evidence clearly shows this. The engaged student in problem posing and problem solving in classroom could have a positive influence on students' achievement, a positive influence on their attitude towards mathematics, and students become active participants in the creation of knowledge rather than passive receivers of rules and procedures. So we could use a prompt-based kind of way to teach mathematics. And in fact, we could give students challenges. In fact, the greater challenge, the greater opportunities we provide for students learning in mathematics. Okay, let's go to the fifth one now. Teachers are at the heart of improving students' learning, but adequate support must take place. Now, I'm sure that Jianping has done lots of studies on those. So I'm going to just give you a little bit of snapshot from what we did to make this point. Okay, so we worked on NS-funded project. In one of the studies, we engaged in the 10 schools. 10 school districts, 10 school districts. It's 20 middle schools and 12 high schools. So I'm going to just show you a little bit of data from the 20 middle schools. Okay. PA means Pennsylvania, NJ means New Jersey, in the New Jersey. So we did a survey. We called it Where to Reform, based on that 4 areas. Okay, 4 areas. So the where to reform is based on that 4 aspects of the responses we received. So here's the results. Let me explain to you a little bit here. So the bottom is the composite score for so-called will to reform, and the y-axis is the difference from the pre-test to the post-test, but standardized. Okay, so which means that if it's 0, it means that from pre-test to the post-test, there is no change. And 1 dot means 1 school. So we use school as a unit, in this diagram. So from this diagram, we could see that the will to reform scores are higher, the more likely the school that would improve through the treatment. And we did a similar kind of analysis, but in this case said for each school we have a control group, we have a control school. So this we standardized the changes of treatment group and the control group. So which means that we standardize the treatment growth minus control growth. Then we plot this here. Again, bottom is the will to reform composite score, and the vertical is the growth, the standardized. So if it's 1, means that 1 standard deviation higher for the treatment group for this. So same results we got. Okay, so this will to reform turned out to be the very good predictor for the identified schools which really work. If we take out this will to reform that factor away, we integrate all those 20 middle schools, the data together, it's a wash. There is no effect at all over the 4 years. Okay, so that's really getting to the point is that, when we do the teacher professional development, we not only need to provide all different strategies and knowledge, but there is another key component there, is their beliefs, their buy-ins. And currently we are working on a research project. We just started in this August. We want to support teachers to teach mathematics through problem posing, and to longitudinally examine how this support for the teachers will impact on their classroom instruction and eventually their students' learning. So this is the model we use in this PPBL project. So through the teacher learning, we hopefully will change their classroom instruction. Because the change of their classroom instruction, they will change what the students learned and learn better. Now, in this teacher learning, in this project, we not only focus on the problem posing instructional strategies, but also we heavily emphasize on the teachers' beliefs about the problem posing, about the teaching mathematics through problem posing, and let them buy into it. So that's we just started this project, but that's the point I'm making. Teachers are in the heart of the educational improvement or educational reform. And we have to do those kind of adequate support in order to make it work. If they didn't buy into it, could it be potentially getting the results even worse in terms of students' learning outcomes? All right. So according to we decided time, and I will use a few minutes to finish up the last point. Okay. Then we will have some discussion. Okay. So last point is about parental involvement. I don't know how many of you are the parents in this talk now. As a father of 2 children, I find it's very difficult to serve as a father, as a father. Be a professor, I got so many years training. I even got a PhD. To be a father, I didn't get a one-day education to do so. But there's so much studies have been done, to looking at the effect of parental involvement. So myself, I involved in a few studies, and actually it's cross-national studies. I looked over the parental involvement in US and China, In our study, we identified the 5 potential roles parents could play in their children's learning. The first one is called a motivator. Second one called a resource provider. Third one is called a monitor. And the fourth one is called a content advisor. And the fifth one called a learning counselor. So our study shows that the results are quite consistent between the two groups of parents in the 2 nations. And the important the finding is that, well, the parents as a motivator, resource provider, and monitor are much more important predictors for students' achievement than they serve as content advisor and learning counselor. Now, this is the indirect kind of involvement. And those could be directly involved in their learning to help them to tutor them, to help them to analyze the learning difficulties. So as a parents, it's the better one to play a role is to motivator and resource provider and monitor. Instead of have to directly get into it. But that didn't mean that parents should not tutor students or help them to solve the mathematical problem. That's not what I'm saying here. But it means that other roles even could be more important to predict their achievement. And I'm going to say that one more snapshot of a recent study, then I will take questions for that, okay? So recently we did another study, which is quite by accident. Now this study is done in China. And so this study is that we looked at the students' perceptions about their parents' achievement expectations. So if we take a step back, in the literature shows that the higher parents' expectations in education in general, the higher students perform in mathematics or in science or in reading. Now we have enough the studies showing that. But in this particular study, in addition to ask the students' perceptions of their parents' general education expectations, we also asked their perception of parents' specific achievement expectation in mathematics. But the interesting finding is this. So here are the different kind of perceptions, okay? So students think that their parents expect them to be on the top 5 in the class in mathematics, or top 50, or class average. But then we find that there is a group of the students say that their parents didn't have any specific expectations. They didn't have any specific expectations. So then we look into this group of the students with they didn't perceive any specific expectations from their parents about the mathematics achievement. So turns out their math-related beliefs is much more positive. And same thing in terms of their perceived math grades is also significantly higher than other groups. other groups. So this study, this finding is very unexpected in a larger project. So we immediately replicated the study, and we found the same thing. If students didn't perceive any specific parental expectations in math achievement, they tend to be more positive in beliefs in mathematics and tend to be perceived ranked their own math achievement higher. So we try to understand why that's the case. And so we interviewed the subset of the parents and the students, try to understand. And so it turns out it's really the parents, every single parents have very specific expectations for their math achievement. But somehow the students or the children didn't perceive any kind of expectations from their parents. And the other students perceived specific expectations for their math achievement from their parents. They usually feel like stressed out, in order to meet the parents' expectations. So now this is the model we developed in the study. So this is still haven't fully studied yet to follow this model here. But the key message is that it's really depends on how parents convey their expectations, either words, actions, or something, and how students perceive such a message. And they interpret this expectation when they receive that message. That will be impact on their beliefs and achievement. So at this moment, it's the middle three aspects haven't fully studied yet. So hopefully in the near future, we could try to study, what is the best way as parents to convey our expectations. It is really impossible for us as parents don't expect something from the students in their education, in their achievement. But how to convey that kind of expectation so that students will receive it, not only wouldn't be stressed out, but also be encouraged for that. All right, so these are the 5 insights I'm sharing with you today. And to end, I want to use a poem to the children learn what they love from Dorothy to end this talk. So I'm not going to read it. Okay, I provided both English and Chinese, and Chinese translation is that I done the most, and I hope it's accurate for that. For the main message, as a closure, as a summary, I want to convey is that we do, regardless of what we do and what strategy we use, our focus is always on the children. But even in the teach mathematics, we need to develop children as a whole. So hopefully they would be live within a encouraged kind of environment. Hopefully they could live with the friendliness. They learn the world is a nice place in which to live. Thank you very much for the time. And so I just stopped here.